Can everyone hear me?
Yes.
Okay, cool. So thanks, Grant, for the introduction, for hosting this meetup. Thanks, Digital Garage, for having us. Thank you all for taking time out of your Sundays, sacrifices. So I'm here to talk about AdChain. I've been working on this project along with Consensus and MetaX for the last 6 months. We aim to solve the $16 billion ad fraud problem. So why should we care about AdChain? Ad fraud is estimated to be a $16 billion problem in 2017. Advertising has been 1% of the United States GDP for the last 100 years, which means that advertising is a zero-sum game. To put this in other terms, basically the cost of telling people about the stuff that you want to sell them is like 1% of the cost of the stuff. And all of the advertising spending that is spent, it remains relatively constant. So if you're not spending money in one place, you're spending it in the other. So for us, this means that ad spend going to fraudsters, right now could be going to legitimate publishers. So just a shout out to my colleagues. Mike, I don't know what's going on. I might shut off my mic if it gets too
probably
bad.
because you're near the speaker.
Yeah, feedback.
If you point that thing away, maybe you'll...
I think it's the EMP.
Try this.
There you go.
Is this better? Yeah, cool. Okay. I don't want to do a software update. Okay, so this AdChain project has been a partnership between the Consensus, MetaX, and the DMA. So Mike Golden, engineer at Consensus, Mark D'Agostino, enterprise at Consensus, James Young, and Ken from MetaX, along with the DMA, who's our industry partner. Together we've made AdChain. So the AdChain is the one on the left, the one on the right is an ad token. So when you guys think about ad fraud, I want you guys to visualize like a bored 16-year-old in Ukraine who basically spins up a fake news website, takes a bunch of RSS feeds, points them to his website, imports them, and has a bunch of content about Trump, and then goes and spins up a bunch of botnets on data centers, and then points them to his fake news site and rakes in the advertising dollars. And then what he'll also do is he'll go and he'll point this botnet and he'll take it to like to Amazon and like fill up shopping carts full of plasma screen TVs so that advertisers think that this is like a high value advertising target. And then they'll spend even more money on his fake news site, of which he takes all of it. Right? Now, the reason that this problem has grown to be so big is because incentives in the advertising industry are misaligned. So here we have our hacker, and then he put up a fake news site, and he's getting all this bot traffic, but then you have this supply chain between the advertiser and the fake news site, where the DSP stands for demand side platform, so they're an aggregator of advertisers. The SSP is a supply side platform, they're an aggregator of publishers, and all of these intermediaries are paid based on impressions on a CPM basis. And so their incentives are something like this. When they are accused of peddling fraudulent advertising inventory, they're like, what fraud? I don't see any fraud, there's no fraud here. It's all great, but the advertisers, meanwhile, are like, what the fuck? This is a big problem. We are getting robbed. So we've tried to solve this problem with the blockchain, Ethereum specifically, and the industry response has been something like this, right? It's like you know, what gives us the right to say we can solve advertising fraud using the blockchain? What magical powers have we inherited or are we tapping into? And in fact, we do have some magical powers. For the first time in history, we have programmable money. And programmable money is really interesting because if you can program money, you can program incentives. And if you can program incentives, then you can sort of program human behavior. So what AdChain is, it's a decentralized whitelist of non-fraudulent publishers, right? So it might be obvious from this slide that the problem here is eliminating these fake news sites, right? So if only everybody were able to agree on which sites were fraudulent and which sites were not, then we would have our answer. The problem is that we can't, because nobody trusts anybody in the advertising industry. And so the way we've tried to solve this problem is using a decentralized whitelist. And to maintain the integrity of this decentralized whitelist, we have an incentivized voting system to maintain it. And AdChain, it's also important to keep in mind that this is basically an experiment. We have no idea if this will actually work, but we are going to try it anyway, because if it does, that would be amazing. So how many of you have heard of BAT? Yeah, so many of you might be thinking, why did we make another advertising token? And I hope, throughout this talk I will be able to convince you of AdToken's utility. So this is how the AdChain registry works. You have some website, some publisher, and they have to apply to join. And along with their application, they submit an AdToken deposit. So in this case, we've set the deposit to be 100 AdToken. Right? Now, once they have applied, any other AdToken holder in the ecosystem can submit a challenge matching that deposit. This starts a challenge period. Right? So if there is no challenge, then the publisher is accepted into the registry when the challenge period expires. Right? If there is a challenge, then an AdToken vote determines the outcome. So you can see in this picture, you've got, site.com is applying. There's a challenge by some safety vendor. Safety vendors basically partner up with advertisers to put tracking JavaScript on pages to detect bot traffic. So they're the most informed in the space about who's fraudulent and who isn't. And then you can see that we have this AdChain registry, and the little cut on the right indicates that this is a smart contract. And so you can see that the New York Times is in. They have made it into the AdChain registry. Foobar.net has been rejected, and site.com, it's a question mark because it's going to a vote. And then we have a simulated vote on the right, which is simplified, but it has some addresses, how many tokens they have, and how they're voting. So to go into a bit more depth about the voting process, it's a majority rules vote where one ad token is one vote, so it's token weighted. The deposit of the losing party is split between the winning party and the majority voters. So that means the applicant and the challenger basically go head to head, right? And only one of them gets their deposit back, right? So the third point is the winning party receives a special dispensation, and in this diagram we've set it to 50%. The special dispensation is the amount of the loser's deposit that the winner gets. The remainder is distributed to the majority of token holders. Right? So if the publisher wins the vote, they're accepted into the registry. If the publisher does not win the vote, then they are rejected from the registry, but they may apply again and deposit ad token and potentially lose it as many times or as often as they would like. So this gives ad token a virtuous incentive structure. Right? Ad token holders rationally seek to increase the value of ad token. The value of ad token is a function of its demand. The demand for ad token comes from the application process and voting process around the AdChain registry, and the incentive to join the registry comes from its perceived integrity. Advertisers want to advertise on the websites of publishers who are in the registry and who have been vetted by the ad token holders. So as a publisher, I want to join. Now, strategic ad token holders will vote to maintain the integrity of this registry and expel fraudulent entities because that is what gives ad token value. Now, many of you might be thinking, okay, this game sounds great, but nobody's going to use it. Well, to get around our cold start problem, we've partnered up with the DMA, and we have a centralized bootstrapping period of 1 year. So the DMA is the Data and Marketing Association. They're a major advertising trade organization. They have 1,400 active members on both the demand and the supply side of the advertising ecosystem. We are giving them exclusive control over the AdChain registry for 1 year, during which time they are able to populate it with their own members. Now, at the end of that year, they lose all special privileges in the registry and everything goes to a vote. as in, so anybody can apply to be a part of the registry, anybody can issue a challenge, anybody can vote. So that's sort of, excuse me, sums up AdChain, the registry portion of it. You can think of, so let me just go back, actually, yes, it's fine. So you can think of AdChain as sort of an identity solution, right? It is a decentralized certificate authority for determining your identity as a non-fraudulent actor in the advertising ecosystem. Now, layered on top of this base identity layer, we can build other types of solutions for other types of problems. So I'm going to now talk about ad markets. So this is our state channel implementation for AdChain. And using ad markets, we are aiming to solve the discrepancy problem. So the problem is that discrepancies in tracked impressions commonly reach up to 20%. So what I mean by discrepancies is, if you look at this diagram, you see that if the DSP is getting paid by the advertisers based on the number of impressions that they report up, they have an incentive to report up that they had more impressions than they actually had. And everybody who's paying based on the number of impressions has an incentive to report down. So in this diagram, we see that the DSP is telling the advertiser that they had 200 impressions, but they're also telling the SSP that they had 150 impressions. And the way these discrepancies are resolved is basically just power-based negotiations. And these happen throughout the entire industry and take up a lot of everybody's time. And we can solve this problem. The way we solve this problem is by tracking all of the impressions in real time. So the thesis for this is like, all right, all the Bitcoins are accounted for. This is great. There's never any confusion about who has which Bitcoin. So what if we were able to apply that same technology to track impressions? Then there would never be any confusion about who had how many impressions. So our goal is to reduce the impression discrepancies to 0 across the entire industry. And it's basically just bean counting on steroids, right? So we track impressions in real time in state channels. You can think of the state of this state channel as an impression ledger between the demand and supply. The channel is updated with every impression, and it creates a tamper-proof historical record of all impressions that have happened. So on the diagram you see, there's some demand, some supply, and I'm using demand and supply as the sort of abstract terms. Demand represents anybody who is buying ad space, and supply is anybody who is selling ad space. So ad space is like some empty rectangular box on a website, or 2 seconds of video that is itching to be played for some audience. That is supply, right? So you want to fill those empty boxes. That's your inventory that you're selling. Okay, so in the channel, this is the version 1 most rudimentary implementation. In the channel, we're tracking the impression ID of the latest impression, the price of the latest impression, the total balance of all impressions thus far, the total number of impressions thus far. And you can add things like the creative ID, which is basically like you can track which ad was showed, and you can track other metadata too, but I left it out for now. And the previous route. And so this idea of routes is important. The Merkle route, as I show, is a unique fingerprint computed from the channel state. And when you update the channel, the demand will sign this newly updated channel state and send it to the supply. And this is how they acknowledge the impression. So how many of you guys know what a Merkle tree is? Okay, less than half. I'm glad I included this slide. So a Merkle tree is a way of creating a unique fingerprint for a data set that allows you to very efficiently discover if one of your original elements of that data set is a member of that data set later on. So let me show you how it gets computed. Actually, I have to ask, how many of you guys know what a hash is and how a hash works? Yes, almost everybody. All right, cool. So in this Merkle tree, we have 4 data blocks, 1 through 4, and then what we do is we create the leaves of the Merkle tree. So we have the hash of each element, And so that's going to be some alphanumeric 32 byte, if it's like SHA-256 or something, string. And then you keep on combining the leaves until you get up all the way to the root. And the highest hash is called the Merkle root. And so the way you combine the hashes is you take the hash of, as you can see, you have the hash of 0, 0 and 0, 1. So you concatenate those two hashes, and then you take the hash of that. And then you do the same on the next part of the tree and the next part of the tree. And so every level you should have n over 2 branches or, elements. So sometime later, let's say you have one of these elements of your data set, and you want to prove that it is in the actual root of the tree, right? So the way you can do this, you can do this using only log base 2 of the number of the elements in your original set. So if your element in question is number 10 here, this is what I want to prove is in. The elements in the proof that I construct, and so you can think of this proof as an array of other elements or hashes that I need, then I can prove that it's in. So the first step would be I take element 10, which is my starting element, this is what I want to prove. Then I would need element 11, which is in my the first element of my proof. And I would take those and I'd combine them and I'd hash them together, and then I'd get number 5. And then once I have 5, I would need number 4. And so number 4 is going to be the second element in my proof. And then I take 5 and 4 and I combine them, then I take the hash of that, and then I get 2. And then once I have 2, I do the same thing with 3, and then I have the root, and then I've proved that number 10, element 10, is actually a member of this root, and I've done it using only 3 pieces of data. So this is efficient. I'm going to come back to that, especially when I do the code review. Merkle roots and Merkle proofs, this is basically like how all blockchains work. It's like a critical concept to understand. Okay, so back to ad markets, right? So I have a smart contract. It's called admarket.sol. I've done a simplified version of it here, where basically it has 2 sort of categories of functions. It has a registry of its members, where I can register some demand, I can register some supply, and then I manage the state channels between them, right? So I can allow that. I have functions for opening a channel, for checkpointing a channel, and for closing a channel, right? And so you can think of the utility of these channels as the sort of representing the business relationship between an advertiser and some supplier, some publisher, right? The advertiser and the publisher, they negotiate some deal, and they say, yeah, it's called an injection order, I think, or insertion order. And so they negotiate this deal, and then they say, all right, I will buy up some of your inventory at this rate over this next period of time, and all of that will get tracked in the state channel. The other thing that's cool is that because we're using Merkle roots, you can checkpoint this data on-chain without exposing any of the data, because you just only checkpoint the Merkle root itself. And the Merkle root contains all of the data in the channel, so you don't actually need to checkpoint or make public any of the channel data. So just to give a little bit more visualization on how this works, let's say at t0, I have a single impression, right? So this impression has an ID of 1, has a price of 1, and that means that cumulatively I have a balance of 1 and an impression count of 1, and the previous root is nothing, because this is the first impression. And so I take all of this and I combine this, I create a Merkle root. So I have my impression ID, price, this is an array, and then I combine them into the top hash, which will be that Merkle root. Then at time 1, then I have a second impression, right? And now I want to include this in my, create a channel update for this impression to represent the newest state of the channel, right? So now I have the impression ID is the number 2, because that's the ID of impression, the next impression. The price of this one is 2, and so the total balance is 1 plus 2 is 3. The impression count, however, is still 2, because there's only 2 impressions. And the previous root points to the root of the original first state. And then I compute from all of these elements the new Merkle root. And so you can think of this sort of works basically how a blockchain works, right? You have some data and then you include the hash of the previous data and this creates a chain, right? So now by creating this chain of all of our impressions, we can use the latest root hash and checkpoint that to the blockchain, and that becomes the unique identifier not only for that state, but for the entire historical record of all of our transactions. And so when we checkpoint this to the blockchain, we are both committing to this entire history of our transactions. Okay, so there's a problem, and the problem is that as a demand, I am the one who always has to acknowledge that the impression happened. And so what if I run some kind of script that's like, you know, let's shave some impressions off of this guy. I'm going to run the script, I'm going to say every 10 impressions, just don't report it. And I would have the power to do that. And so to combat that, we introduced the ad market as a neutral, passive, third-party observer that's only there to break ties. This is like the minimum amount of trust you need to allow these two parties to coordinate. Right? Normally when you think of like what an ad market or an ad exchange does, it intermediates the transaction and it takes some cut of all the throughput. The ad market would just be watching, and it does nothing to intermediate the transaction, but it just voices its opinion if there is a tie and it needs to break it. So we have this game, and this game has 3 parties. And so it's a coordination game between the demand, supply, and ad market. So this is how the impressions will get tracked, right? The objective is to record an impression if at least 2/3 of the people saw it. So this is how it works. First thing that happens, right? And so I have this web page. It's got a video player on it. After 2 seconds of the video playing, of the advertisement on the video playing, I'm going to have this impression event, and it's going to be sent out to all of the participants. The demand, supply, and the ad market, they're all going to get this impression served event, right? And then what we're expecting to happen is that the demand here is going to send both the supply and the ad market a channel update, which says, I acknowledge that this impression just happened, right? And if they do, everything's great, and we can move on to waiting for the next impression. However, what if they don't, right? So what happens if I'm the supply, and I'm waiting there, and I'm waiting there, and I just saw the impression, and the ad market, the demand has not yet told me that they have acknowledged that impression. They have not yet sent me their signed channel update which acknowledges that that impression happened. What am I to do? You know, maybe I'm like, all right, you know, I'm giving the benefit of the doubt, but enough times of that, you go to the ad market, right? So I go to the ad market and I say, please, ad market, did you see this impression happen? If the ad market responds that they did, then they will either they will send an ACK or they will send a no ACK. And so their acknowledgement would be them signing the impression ID, right, of the impression that just took place. Right? So if they saw it, they send this signed impression. If they didn't see it, they don't. They say, I didn't see the impression. Right? So then the supply, if they get back that the ad market didn't see it, then they have to accept that they're the only one who saw this impression, and they can do nothing to convince the other 2 people that the impression actually happened, and so they drop it. On the other hand, if the ad market responded that it did see it, then what the supply will do is it will go to the demand and say, hey, I have proof. The ad market also saw this impression, and I would kindly request that you provide me with a channel update acknowledging this impression. Thank you very much, sir. And then we'd go to the demand, and the demand can do one of 2 things. And they can either say, yes, all right, I comply, I will send you this impression, I will send you the acknowledged update, and if they do that, everybody's happy. If they don't, then, well, they broke the rules. And if they do that, automatically, the supply will just close the channel right there and then. So that's how the high-level server-to-server communications work for making sure that we can keep the entire advertising industry in sync with the number of impressions that they all claim to receive. There's another part of this, which is checkpointing. And so this part is different than what you guys just saw. This is about being able to make commitments on chain to the transactional history, checkpointing, but doing it in a way such that you only need to expose data if there's a dispute. This is more simple if you don't have a privacy concern, but it's more complicated if you do, and we went with the slightly more complicated version, so you all get to enjoy that. So the first thing you do is, between the two people, you open a channel, right? And then some time passes, you have some number of acknowledged impressions, you have this chain of impressions, and then you want to checkpoint that. Right? So either party at that point can propose a checkpoint. And I listed all these with the little function calls just to indicate that they are functions on the smart contract. Right? These are methods on the contract that are getting called. Right? So I would call propose checkpoint, and I would pass in the latest checkpoint data and the signature to prove that it's there. And then after I do that, there's a challenge period that is triggered. And so during this challenge period, the other party in the channel can attempt to challenge what I just proposed, right? Why would they want to do that, right? So let's say I'm the demand and I'm paying the supply, right? So we have some impression chain that I'm supposed to pay them for like 100 impressions. And instead what I do is I checkpoint the state where I only owe them 50 impressions. All right, so the supply notices this and they say, well, this is bullshit, I'm going to challenge that. And so then what they would do is they would provide the state with 100 impressions, and then because my initial state, I only provided the Merkle root, I didn't actually expose any data, the supply, they have to prove two things, right? They have to prove, one, that I've signed this later state because I'm the demand, I'm the one who's signing, and then they have to prove that the number of impressions are higher than in the original state that I proposed to check. And so I'm using the impressions as a sequence number. If you've seen some of the other material on state channels, you'll be familiar with that term. If not, it's totally fine. The important thing to know is that it only goes up. So if the challenge, so in happy case, if the challenge period expires, then that originally proposed state is recorded on the blockchain forever. If a challenge is issued, then we go to the next step, which is either I, as the demand, can accept this challenge, or I can let the challenge period expire. If the challenge period expires, they win, and what the state that they proposed is what is saved onto the blockchain. If I accept the challenge, the way I accept the challenge is I show that the number of impressions in my original state that I proposed is actually higher than in the one that they challenged with. And in both cases, I would provide the Merkle proof because I'm just checkpointing that root. So I provide the proof that says, here's my impression in the tree, and here's the set of hashes that you need to prove that this number of impressions belongs in that root. All right, so now I'm going to go into a bit of code. Am I doing on time? Good. Cool. All right. Can you guys see this in the back?
Yeah.
Bigger, smaller? Bigger? Bigger. We can go bigger. Is that good? Bigger? Oh my god. Yeah? I'm seeing head nods. All right, cool. I'm gonna grab a drink of water. Okay, so this is the channel code I was just talking about. I'm going to apologize in advance because you're probably not going to get all of this. I'm going to go through it and I'm going to do my best, but contracts are complicated and state channels are like complicated on top of contracts being complicated. Okay, so this is the ad market contract. This is the contract declaration. It is EC verify, which just means it imports a function that allows me to verify signatures more easily than having to declare it in my code. I have this empty string, which is just a constant. It turns out if you take the hash of the empty string, that's a result. Like many contracts, this contract has the idea of an owner and an owner URL. And the owner URL is, so this is an ad market that's deploying this contract, and so it will say, this is the URL that you can send me channel updates at. Okay, so this, there's a few functions or data sets for the registration part, right? So I have some number of demand that I'm registering, I have some number of supply that I'm registering, I have to keep track of all of them. The reason it's a mapping of address to string here is because I'm storing them by their address, but the string that I'm storing is their URL as well. So this is where to find them. So you can imagine you have some registered demand, and this points to toyota.adserver.com. You have some registered supply, it points to some NewYorkTimes.adserver.com. Then I have to store the data for all my channels. So this is going to be a mapping of bytes 32, which is the channel ID, and it's going to store channel metadata. Then also for each of my channels, separately, I'm going to store any challenges that are outstanding for the checkpoint process. Then I'm also going to store a nested mapping, which says for each demand and for each supply, do they have some kind of channel open already? And if they do, then I check that when I'm creating a channel so that I don't make duplicates. I have a channel count, which I increment, I go up. I have a channel timeout, which is the maximum lifetime of a channel in blocks. So after that, you can clean up, you can close down channels that have expired. You don't want to just have a lot of dust, empty channels sitting around. You have a challenge period, which is, these are all global constants. So these are the number of blocks to wait for challenges before closing the channel. And then you have an enum of the possible channel states, right? So the channel is either open, it is checkpointing, it is closing, or it is closed. This struct channel stores the metadata for each individual channel. I have state variables, which are part of every channel update. And the reason they are part of every channel update is because you need them to figure out what channel that data belongs to. And so there's a type of attack called replay attacks. So for example, if I didn't have the contract ID or channel ID, then if this same two people, demand and supply, had a channel on some other contract, then they would be able to use signed state updates in this, and they would be considered valid on that other contract. And so there's more there, but I'm going to keep going. Then you have metadata. So for each channel, you store what state it's in. This is the checkpointing open, close, and close that I talked about. You have the expiration for this current channel, the number of blocks after which this channel expires, and then you have the challenge timeout. So the number of blocks after the state for this channel can be finalized if there's a challenge, and then a proposed route. And so the proposed route is when I'm checkpointing this channel, I will propose a Merkle route which contains the entirety of the state to checkpoint. So just to reiterate here in my comments, I've got route is the Merkle route of the previous route in the current state. You guys saw this. It's impression ID, price, impressions, balance. In case of a dispute, this data is made public and verified on chain using proofs. So then I have the challenge route. So this is, if I'm issuing a challenge, then I have to also keep track of what is the root of the challenge and how many impressions went along with that challenge. All right, modifiers, I'm going to skip that. Some events, some to-do events. All right, so you constructor, basically when I deploy this contract, I have the owner is the sender of the message. They supply their URL and the global constants. They can update their URL. I have the registration functions, which basically says only the owner can call these, and so only the owner can register you as a demand or as a supply. You have to provide a non-empty string. That's why we have that hex, because the isEmpty string takes the hash of that string, and then if it matches the empty string hash, then it's considered invalid. We also have methods for deregistering, so it basically just sets the URL to an empty string. Okay, once you are registered, you can change your string to anything you want. So if you update your ad server, you can change to a different ad server, except if it's empty. Okay, so that's all great, but state channels, right? So we want to allow demand to open state channels with supply. So in our model, you just have demand that's the one who's opening channels. This sort of maps to how business deals are done in advertising today. I will go and I will get this insertion order to earn the right to advertise on your inventory, right? And opening the channel doesn't mean that you have to acknowledge or send, sell me any of your advertising inventory. It just means that I'm interested. And then you would have to either programmatically or manually go and update, who the list of advertisers is that you send bid requests to include me as the demand, right? So, okay. There's some conditions that must be met in order to open a channel. First, you check that the supply that you are trying to open a channel with is registered, so you have this address supply. Then we have, we check the channel partners to make sure that we don't already have a channel open with this supply. Then we increment the channel count, take the hash of that, and that becomes the ID of this channel. We have an expiration date, which is this channel will expire at the current block number plus the global channel timeout. And then we save all of the data to the blockchain, right? So we say channels, we store this in, channels is a key value store, so we're storing it by the ID, which is, channel ID is the key. We're creating this new channel struct. So if you remember up here, we had a channel struct, which had all these variables. It's the container for an individual channel. Well, we're creating a new instance of that, and we're saving all of this data. So we save the contract ID, we save the channel ID, the address of the demand and supply, the root of the channel, which starts at 0 because there's no state. And then the channel is open, it has the expiration, etc. Right? And then we say, we keep track that these two people now actually do have a channel together. Okay, so some time passes. We want to checkpoint this channel. So the first thing that happens is either party can propose a checkpoint. To propose this checkpoint, they include the ID of the channel they want to checkpoint, the proposed route that they want to checkpoint, which contains all the state, or is the unique identifier for the state, the signature, which has to be from the demand acknowledging that state, and a flag rule renew, which is do they want to, at the end of this checkpointing period, to keep the channel open, or would they prefer to close it? Okay, so what you do is you fetch the channel from your storage, so this will be the same channel that you just set before. Then you will check that, make sure that the sender of this proposed checkpoint is either the demand or the supply that was part of this channel. Then you will check that the channel is open, which means that the channel is not already checkpointing, closing, or closed. And then you will do this fingerprint, which you will compute, which takes the SHA-3 from the address of the contract, the channel ID. So this fingerprint is important because this is what is getting signed every time you make a channel update. Right? So I compute that from the ID and the demand and supply and the root. And then I run my EC verify function, which will return true if this fingerprint matches the signature, which matches the address of the demand. The fact that we can check signatures in contracts is what makes this whole thing really easy and makes it work. So if the signature passes, then if we are renewing the channel, then we set the channel state to checkpointing. If we are not renewing the channel, then we set the channel state to closing. And then we set our challenge timeout. So we start our challenge period, and we set some block in the future at which the challenge period will be over, and either party can close this channel. And then we save the proposed route, which is our state. Okay, this is a little helper function, and so this is just in case you started out and you were checkpointing a channel, and then really you change your mind later, and then you would want to close the channel. You would call this close channel, and all this does is it changes that renew flag. Well, you don't use the renew flag. It changes the channel state from checkpointing to closed. So you check that one of the two people who are closing this channel, belonging to this channel, send a message, and then you check that the channel is currently checkpointing. If that's the case, then you would set it to closing. Okay. So now I want to talk about challenging. So if either the supply or demand can challenge a checkpoint that is in progress within the challenge period, so they would supply a different Merkle root. This will be the challenge root. They provide the channel ID to look up to get the channel data. They would provide a number of impressions. They would provide the index, which is the index of the impressions in the array of data that constitute the state. So if the impressions is like the third item in the state, you would say, well, index would be 2. And then the Merkle proof, which is all the other hashes you need to show that this impressions matches that challenge root. And then signature of the demand, right? And you go do your checks again, fetch the channel, check that it's one of the 2 people who started the channel, check that the state is either checkpointing or closing, check that the challenge period hasn't expired, recompute the fingerprint to make sure that the signature matches, and then we call this check proof ordered function, which I defined down here. This check proof ordered function is what determines, it validates the Merkle proof in Solidity. So it takes the index of the hash of the element that I'm trying to, so it's going to be the impressions count, and then I construct this Merkle proof and I check all the hashes in order until I get to the root. If it matches the root, then it's good, and I return true. And then and if all that checks out, then I save this data, this challenge, in my challenges mapping under the same channel ID for this channel, and I save the impressions as well, and then I extend the challenge timeout to give the other person a chance to respond, right? So if I didn't do this, then I could submit a challenge right at the very end, and then let the challenge period expire, and then really quickly close the channel maliciously, and then I would win. So we don't want that, so we want to give the other person a chance to respond. One of 2 things can happen once a challenge has been issued. Either the original person who proposed the checkpoint will accept this challenge, or they will not. If they accept this challenge, then they have to provide proof that the number of impressions in their original proposed Merkle root is higher. If they succeed, though, then the channel checkpointing immediately completes, and the state that they had originally proposed is saved to the blockchain. So I call accept challenge, I have the channel ID, I have the impressions, I have my own Merkle proof, and the index for the impressions again. Right? So this looks basically the same as the function I just showed you. Do my checks, fetch a channel, do my checks, check that it's either checkpointing or closing, check that the challenge period isn't over, check that a challenge exists, right? So I can only accept the challenge if a challenge exists, and this is where I just previously saved that challenge. Check that a challenge was presented. So this fetches the challenge, and this checks that it was presented. This is just basically saying that the number of impressions in the challenge object has to be greater than 0. If it's 0, then you should throw, and this function should exit. Okay, then we check that the number of impressions that I'm providing is larger than the number of impressions in the challenge, right? If I accept the challenge and then I provide a smaller number of impressions, then I'm not doing anybody any good, and I should exit. Then I check the Merkle proof for the impressions in the proposed root. Again, then if the channel is renewing, if the state is checkpointing, then I keep the channel open. Otherwise, I close the channel. And even if the channel is closed, we save a bunch of stuff to the blockchain. So we save this channel root, the proposed root. So that would be what we save. Otherwise, we set the proposed root to 0, so another person can propose something later. And we reset the challenge timeout, and we delete the open challenge. All right. And so if a challenge was not presented, either originally or later, then we just call the checkpoint channel. So this is, I can do my proposed checkpoint, and then call this checkpoint channel, or after somebody has placed the challenge, nobody has accepted it, I can call proposed checkpoint channel and this will terminate the checkpointing process. You guys got to get you some pizza. All right, we're almost done. So, same checks, right? So we fetch this channel, do our checks, check that it's checkpointing or closing, check that the challenge period is over this time, right? So once the challenge period is over, you can call this, grab the challenge. If there is an unanswered challenge, it wins. The only case there can be an unanswered challenge is that somebody proposed the challenge, and then it wasn't accepted. If it was accepted, it would have been deleted, and the checkpointing process would finish. So if there's an open challenge, that means it was not accepted. And so the challenger wins. Otherwise, the original person who proposed the checkpoint would win. And then the same things for renewing a channel or closing a channel. So if we have a checkpointing, then we renew the expiration and we set the state back to open. If we are closing the channel, then we set the channel state to closed, and we say that the two partners, demand and supply, they no longer have an open channel with each other. So we set that to false, the channel partners line. And that's basically it. So that is that. And so just to prove that I'm not totally bullshitting, I'm going to go to my tests, and I will do, actually, so I'm going to start. So here, this is where I have tests. I'm going to run npm run test RPC. Here I'm going to npm run Mocha. So you see test RPC has started, and then I run Mocha, and unless I have really bad luck, all my tests should pass, and you see I have tested all of these things, and yes. Wait for it. It's deploying the contract, it's building the context, yeah, all the green check marks. That's what we like. All right, cool. I have 15 passing tests for this. This is, in my estimation, about 1/10 of the total number of tests that will be needed for this before it's like production ready. And this is because when you're writing Solidity, all applications are financial applications. So you not only have to test that it works, you have to test every possible case where it could possibly fail.
So that's a lot of tests.
And that's just the contract test. Then there's the off-chain stuff, right? The servers where I was telling you before, I had this game we were playing where people respond, and then you have these interacting asynchronous state machines, right? And so if we go back to the code, I can give a quick demo of that part. So it's just like clear, almost done. This is the last thing. All right, so I'm going to run 3 servers, and I'm going to run a script, right? So here's the first server. I'm going to run node, loader, demand. So this is going to run my demand server. I'm going to run node, loader, supply. I'm running loader because I'm using Babel because I like async await. Add market. All right, so I've done this, and then I run node not in the right repo or directory. JavaScript. So node script. Actually, let me show you what script 1 does first. And then you can see, okay. So let's just like make this a lot bigger. All right. Is this big enough for you guys in the back? Got it. Okay. Let's actually, I'm going to just open this up in a different terminal. Okay, so cd JavaScript vim script 1. Basically, script 1, what it does is I have this function generate impressions. So it's going to generate a single impression, and then it's going to send it to the supply, the demand, and the ad market. So first, it's going to open connections with all these guys, and then it's going to post requests to all 3. So it's going to send the this one is the supply, this one is the ad market, and the last one is the demand, right? So it's going to send these 3. And so this is just scaffolding, right? This is the rough prototype. This is nowhere near ready. But I thought I'd show off anyway. So then for every impression, I would send the impressions. And so then you'll see that this hit all those servers, and then those servers will do what you expect them to do, which is the demand should send an acknowledgement of this impression to the supply, so we'll see that in a second. All right, so let's go back to here. Let's make this way bigger. So now I'm going to do node script 1. All right, so if I scroll up on all 3 of these, so the bottom left, this one is demand, so I received the impression, and then I sent the channel update. This is the channel update. It has the signature from the demand on this, and then these guys all receive the channel update. So everybody's happy. Right? Now if I run node script 2, in this case, the impression is only sent to the supply, right? And so what happens when the impression is only sent to the supply, so here I've received the impression, is that they will go and ask the ad market, did you see this impression, right? And so here, after this, it says signature requested for impression, and then it has the impression data, and it says impression not found. I did not receive this impression. And so it responds that the impression was not found. And this gets a response from the ad market that says nothing. The impression was not found, right? So it drops it. It says, all right, I'll pretend like this impression never happened. Okay. Then you have script 3. Node script 3, right? And in this case, the impression is sent to both the supply and the ad market, and so then the supply gets a response that says, actually, I did find it. So in this case, the ad market responds, impression found. The supply says, signature received from ad market. I received their signature on this event, and then I go to the demand, and it says response from demand received, because demand comes here. It says channel update requested, ad market signature verified, and then channel update sent. So the demand has said yes, okay. I see that you have proof that the ad market also saw this. I will acknowledge that proof. And then the channel update is received, and everyone's happy. And that is all I have to say.
Can we give another round of applause to Ameen? I thought that was super cool.
Should I have questions? Or?
Yeah. First of all, one thing I neglected to do at the start was also give a shout out to our sponsors for this event, Tendermint. They are buying the pizza for this. And
thanks, Jay.
Yeah, is Jay Kwan here? Or oh hey, yeah. So does anyone have any questions? First of all, okay. Do you want to answer them? After the Q&A, Tendermint will be giving a presentation on what they're working on. It's very cool stuff. They also have a hackathon, which you guys should learn about. So, yeah.
Okay.
Cool.
I'm going to kill my mic then.
Yeah.
All right. You.
What is a state channel?
Oh, next question.
So, what is the point of checkpoint.renew, like the renew method when you have a state channel open? Like, why would a checkpoint in a channel, why would you need to renew it unless you're going to close it, essentially?
So you want to, so the reason you might want to renew a channel instead of just creating new channels every time, well, that's the reason, right? You might not want to open a new channel every time and go through the process of like ambiguity where you're like waiting for your channel to be closed and you're like not sure, you're waiting to send the next transaction to open the channel, but you don't want to do it before the old one's closed and you have to switch between the two channels. You're not sure which channel your data is getting recorded in. If you just use the renew flag, then you'll always be confident that all of your data is being recorded in the same channel.
And so is there like a max impression size per channel?
No, you can keep channels open for as long as you are maintaining your business relationship. Yep.
So let's say you have this guy who comes from Russia, and he creates websites, and he has a botnet for his website, and he receives money from advertisers. I don't understand how your solution can prevent him from doing this, because
yeah, so the ad market stuff has like very little to do with actual botnet stuff.
so where's the problem?
Yes, so I'm gonna tell you something else, right? I'm gonna tell you that AdChain does not actually solve the fraud problem. Yeah, right. So
unless the advertisers are on your whitelist.
right. So here's what happens, right? AdChain is actually a system to allow advertisers to agree on what fraud is and where to draw the line, right? So if some botnet comes along, publisher with like 80% bot traffic comes along and is like, I'd like to join the AdChain registry. Anybody who has done business with them or who's tracked their traffic and knows that they're mostly fraudulent will be able to challenge them and make public the data that they have that exposes them as fraudulent and allow everybody else to make an informed vote as to whether or not they think this person should be part of the AdChain registry. Now, I don't know, maybe the industry collectively decides that 80% bot traffic is like a pretty low bar, and they're totally fine with that. And there's nothing we would do. That would be the decision by the industry. That would be that would be the collective will of the ad token holders. Now, I think that won't be the case, because if it is the case, then ad token has a value, so the people who are participating will lose all the money that they put up to participate in this ecosystem. So my guess is that they will be strategic and rational and like aim to only allow applications by publishers who are deemed to be non-fraudulent.
Is there any mechanism for after someone's been entered into the registry to like kick them out?
Yeah, so you have a membership period, right? And so the membership period, we're looking at something like 3 months right now, but it's configurable. It'll probably be determined by a vote. So if basically you can do an exit scam where you sign up for the registry and then you're like, man, I'm going to do a bunch of fraud now and then I'm going to get away with it. This is going to be great. But if you want to renew your membership at the end of that, everybody who you just scammed is going to be like, all right, as soon as this guy tries to apply again, we're going to wreck him. So.
And that's just based upon how many tokens you have.
Yeah.
What if that fraudster comes along and they have 20% of the coins and they just outbid everybody?
Yes. This is what it means to be decentralized.
And then it is bidding, right? Like I noticed you had like 100, 110, and can you arbitrarily decide how many coins you're getting?
So it's not, okay, so I'll stop you there because it's not about an individual versus another individual in terms of the token, right? There's a fixed amount of ad token that you will deposit to be part of the registry. And that's the same amount that somebody who is challenging would need to match, right? At that point, it goes to an ad token vote. And at that point, it's just the majority rules by a token weighted vote. So if somebody has 20% of the collective voting power of ad token, then their vote will hold a lot of sway.
But they have to have more tokens than me in order to challenge me?
No, they just have to have the same amount that you submitted with your application. And that's another configurable parameter, and it will probably be decided by ad token vote. Yes, in the back. Yeah.
What's the incentive for the advertisers to actually challenge?
Yeah. So.
Like I'm thinking about this from like a bureaucratic standpoint. So like, if you can take someone who wants to like eliminate bad guys and like that's a societal psychological typical phenomenon, who want to catch cheaters. But in an organization where they have plenty of resources to deal with, like I can't imagine a department that's in charge of doing this activity. So how do you incentivize that?
Right. That's a really good point, right? Advertisers, they haven't been, throughout their existence, they've never been like, oh, we're just going to participate in this decentralized, incentivized voting system, right? We'll just spin up a team to do that real quick. Right? That's not the case. There are, however, people who I think are the most likely first participants are the safety vendors that advertisers hire. So safety vendors are people like White Ops. The advertisers hire them, and then they run tracking JavaScript provided by the safety vendors to detect bot traffic. So that they'll say, you know, they move the mouse like this is a bot, and then they'll tell the advertiser, you know, the bot traffic, or the advertising that you bought on website X is like mostly fraudulent, and you shouldn't pay them. Right now, the reason I think AdChain is interesting, one of them, is because we actually incentivize the safety vendors to share that data publicly. So right now, if you're a safety vendor, you don't want to share that information publicly. You want to get as many customers for that data as you can. So you want to sell that data as many times over as you possibly can, right? But in AdChain, all it takes is one person to challenge to be able to say, you know, I'm going to get the money from the person who I'm challenging. And so you create this incentive for them to make their case public against somebody who they think is fraudulent.
To some degree, I think the advertisers are incentivized to keep the pool small too, right? I mean, ultimately, if like in an AdSense model, for example, originally when you bid against other advertisers, by keeping other advertisers who are fraudulent off, aren't you keeping that pool small and therefore controlling access to your users?
So the pool is of publishers, not advertisers, right? Anybody who wants can participate. So I'm not sure if I understood your question.
Well, I thought your question was, what's the incentive for advertisers to challenge other ads, right?
Well,
my question is, what's the incentive in general for any of the players to challenge and risk losing tokens?
Yeah.
With an uncertain outcome?
I mean, so if you lose, you lose 100% of the tokens that you deposit. If you win, you get, you know, some portion of the loser's deposit. That parameter, the special dispensation that I described it as before, is very important in determining like your optimal strategy as somebody who's thinking about challenging, right? So if it's set to 50%, for example, then I have to be over 66% confident that I'm going to win the vote in order to challenge. And this is like sort of simple expected value, right? So, you know, I have a 1/3 chance of losing all my money and a 2/3 chance of winning half my money. So I should, if I'm more than 2/3 likely to win, then I should bet.
Then is there an opportunity for, on top of that, to start building like derivatives markets? Because then theoretically, if you have this data, you can actually build like.
Yeah, we should talk after.
So.
Yeah, it's likely that prediction markets about whether or not somebody will actually win a challenge will actually be used in order to figure out if you should challenge.
Right. I'm only saying that because these, so like if you have an organization that's doesn't understand how to properly value the outcome, then there's an opportunity for them to buy some kind of hedging instrument so they don't lose.
Yeah, totally.
Just to add to that, like that negotiation or that challenge, in real life it actually happens just over emails.
Right. Yeah, so we
before
want to
paying the bill, like
Like,
they do challenge, like this is our data, that's your data, and they do the comparisons and figure out the discrepancies. So that's already kind of happening.
yeah. So Shaylee's here from the IAB. We're working with him to figure out if there's synergies between our projects. He pointed out that this already happens, this whole challenging thing about whether or not your traffic is fraudulent. But he said that it happens over email. So what we want to do is we want to take all those emails and get rid of them so that you can just do this once in public in front of everybody and be done with it.
Is there like a subscription fee for the registry? How does that work? Or how does the company make money?
The company?
Yes, is AdChain going to be an organization around it?
So there will be a nonprofit that shepherds the development of AdChain protocols and smart contracts. AdChain itself is not like a for-profit thing. There's companies, MetaX and a branch of Consensus AdTech, CAT, which will build for-profit applications on top of the AdChain registry. So, for example, the ad market that I showed, right, it had a registry for a supply, right? You register supply or something. Now, it's very likely that, in order to be eligible to be a supply in the ad market, you will need to be in the AdChain registry. And so we can build these application layer dApps on top of this identity solution.
To follow up on the whole discussion on incentives for those voters, so you're kind of dependent on like a vendor like White Ops or someone that has best perspective or decent perspective on the quality of the publisher to pull these tokens. And yet this, so ICO is coming up in a couple of weeks. People investing, maybe about this industry. So how does it end up working out that some majority of token holders that participate will have really any knowledge or like some perspective on what is quality and not quality?
So the question is, if I understand it correctly, it's like we're having this token launch in a little over a week. How are we going to make sure that the people who are holding the tokens are people who are like correctly incentivized to play this game, right? There's a thing called Coase's theorem, which is like basically, it doesn't matter the initial distribution. The people who need or are the most incentivized to acquire the tokens will like get them eventually, and it means that that the ending results are sort of the same, but the distribution of wealth becomes different based on how you distribute the tokens initially. There's that, and then it's sort of like I think the progression of this is that we're not going to get the whole industry on board day one, right? There will be a few people who are participating, and in the beginning for the first year. There's no voting system. It's just the DMA has like dominion over the whole registry, right? And so, but what we are doing is like building these value-added services and applications on top that are, by virtue of being on Ethereum and based on smart contracts, they're like very easily interoperable. And so that's an ecosystem that you'll probably want to participate in. And so at that point, you might want to buy ad token, hold ad token, and have some say in what the definition of fraud is in the industry, right? And so it'll start small, and I think it'll grow once people see other people doing it. And I think success for me is like the first time a publisher is like rejected, and they're like, I'm going to apply, and then everyone else is like, no, you are too fraudulent to be in. And then after that day, I'll be like, yes. Did it. Let's do it 100 more times.
Just one follow-up on that. There are enough of these games are being played, like this challenge happens. This needs to happen, I guess, a lot of times before things like it gets to this sort of equilibrium of like real knowledge is being imparted in this process. So, but there's not a whole lot of applications. Like I see it. Applications to the registry. Versus like an impression level, sort of thing, maybe that, just a lot more of these challenges going on. So how does that work out? Like, are you anticipating having like, hundreds of thousands of publishers applying to this all the time? How does that work?
Yes. Yes, we are anticipating putting the entire internet publishing industry on the smart contract.
Mm-hmm. Is there an angle where
Not sure I understand. If your friend is a publisher, can you take advantage of it?
Yeah, like negative SEO type. If I want to crash somebody else, whether it's your networks or their network against the wrong party.
Right. So this is fun, right? What he's saying is like, all right, let's say there's some publisher I don't like. I'm just going to send them a bunch of bot traffic for free. They don't even have to pay me. I will just send them all this bot traffic out of the goodness of my heart because I want them to fail their next membership application in the AdChain registry. Yeah, I don't know the answer to that yet. We're working on it. If you have solutions, let us know. We have a year to figure this out because that's when the voting will start. So, all right, I gotta give it up.
Yeah, I think that about wraps it up. You can talk to me afterwards. And, please welcome Jay Kwan. He's with Tendermint. They're, I think, a little bit one of the under-the-radar blockchain projects, which is totally awesome. And he's going to present. And there you go.
It's not so much a presentation, more like an announcement. First of all, I'm here to make the pizza good, so if you have any feedback about pizza, if you have any ideas about what you want for next time, let me know. I'm here to represent Tendermint and Cosmos. How many people have heard about Tendermint? Or how about Cosmos? Cool, all right. So with the context of this meeting, I'd say that we want to help scale Ethereum. So we have something in the pipeline for Cosmos, which is a bridge to Ethereum. And through the Cosmos Hub, we'll be able to host many Ethereum blockchains that are all connected together, right? So with that in mind, we are hiring. So this is the announcement, one announcement. We're looking for experienced Solidity developers, but also any language polyglot, programming language nerds. Please contact us. And the other announcement is HackAtom. HackAtom is it's going to be an ongoing thing, and it's really for everyone. If you have an idea at any stage, from inception to getting a team and getting it programmed, we can help. So look up HackAtom, which is the Cosmos Hackathon, and we have prizes available. 50,000 ETH will be distributed at the end of 3 weeks, so you have 3 weeks to apply for that. And $50,000 worth of it.
Whoa.
Can you buy it now?
No, we'll figure out the price point. It'll be a fundraiser. That'll be easy. But that's just for just an idea. But and if we really like your idea, we'll help you get it all the way to inception, especially if it contributes to the Cosmos ecosystem. What we care about is open source, new, interesting blockchain ideas. Thank you.
You guys want to help yourself some pizza and